All right, this is going to be a stellar parallax speed run. We got prerequisite information, arc minutes, arc seconds, etc. A degree is a unit of angle measurement equal to 1/360th of a full rotation. That's 1 degree. So if you take a protractor, pretend that's your field of view, 180 degrees across. If you took 1 degree and divided that into 60 sections, you would have each one of those sections would be 1 arc minute. Okay. And then if you further divided each one of those minutes into 60 seconds for each minute, you would have um, one arc second. And that 1 arc second turns out to be 1/3600th of a degree. And then to continue on with the system, if you times that by 1,000, you get into the milliarcs at 1/3,600,000th of a degree. And then if you times that by 1,000 yet again, you get what you get 1/3,600,000,000th of a degree, right? So that's how the system continues and breaks down. For terrestrial observations, you're gonna get into the arc minutes and arc seconds. For the milliarcs and microarcs, that's where they talk about satellite observations and things like that, where they're outside of the Earth's atmosphere, so that they can get the so-called precision that they need to that they can't get due to atmospheric conditions. Because typical atmospheric conditions, no matter how good your aperture and lens and all that stuff is, you can't resolve anything finer than 1 arc second, and that's on a really good night. Most typical nights, you're seeing 2 to 3 arc seconds, according to mainstream sources. So, moving on to stellar parallax. When you Google stellar parallax, you're going to see um, the quote unquote basics of what it looks like. You got the baseline of a triangle here. So you take an observation at some point in the year, and then 6 months later, when the Earth has rotated to the other side of the sun due to its orbit, you will take another observation of the same star and compare it to background stars, and that will give you parallax. That's what they're telling us. So we have 93 million miles times 93 million miles. They've established in 186 million mile baseline for a triangle. They take their measurements, and you're like, oh, okay, cool, checks out, looks like a triangle, everything makes sense. Now, keep in mind, measuring parallax is a real practical thing. It has practical application, and what you can typically do is once you have your baseline established, and accurate, you can measure the angles between distant objects by closing your left and right eye, respectively, where you go and take your angles. And using that information, you can extrapolate a good estimation on the size of the distant object or the distance to it. Now, the thing with that is you have to use, reasonable angles, right? Like, see how these are all reasonable triangle angles? Was that like a 45 and a 45? Kind of going up. So it's like you have to have, reasonable angles. And the reason for that is the the smaller or larger your angle, the wider, or the larger your margin of error is, right? So you want to keep it within a nice range. That's what's recommended when doing regular terrestrial parallax observations. So moving on, we're going to take a closer examination of how they do stellar parallax. So the distance to an object can be determined by its parallax angle, where the distance is proportional to the parallax angle. Specifically, the distance in parsecs is equal to 1 divided by the parallax angle in arcseconds. 1 parsec is equivalent to approximately 3.26 light years, so an object with a parallax angle of 1 arcsecond would be located at a distance of 1 parsec, or approximately 3.26 light years away. So to give a kind of example what this looks like, so as we were talking about earlier, you take your observation, Earth orbiting around the sun. 6 months later, you take your observation, you're building your triangle. This angle here is your parallax angle. So the baseline of your triangle is going to be the way it's going to work out with these fine angles is this angle is going to be really, really tiny. So these angles are going to be really, really big. So to kind of continue on, what that looks like, the further something away is, the smaller its parallax angle is going to be. If it's closer, it'll have a larger parallax angle. So you can kind of see the triangle here is, would have a larger angle than something that's further away. So what they do is they come up with this noble ladder system, right? Where they say like, well, we've confirmed the distance to this object, right? We know the distance to this based on, its brightness and magnitude and all that, right? So they use that system uh, to like as their first stepping stone for their parallax. So they say we know based on the brightness of this star that it's this far away, and then using that they they further the distance out. They take their parallax, they compare it to what they quote unquote say that they know and have established, and they go, okay, so now we know that this star is this far away. So they've now extended their ladder. So let's say that there was a star here, at a brightness of whatever, and they said, okay, for it to be this bright, it has to be this size and this far away. So they quote unquote know that the distance from here to this hypothetical star that I didn't put in the slide, just kind of rolling with it, would be whatever, right? And then they would cross reference that with the parallax from this, and they would go, okay, so they would then extend their ladder another step, and they can now say that they can measure things within this distance. So then to get out to here, they build upon that, get the angle, cross-reference it all right, and they've got this ladder. This is how their ladder system works. So quick recap, parallax angle right here. The closer something is, the bigger its parallax angle will be. And to just kind of give a further example of something with a smaller parallax angle than one arc second, we'll do distance in parsecs equals 1 divided by the parallax angle in arc seconds, plugging in the parallax angle of 0.008 arc seconds, we get the distance in parsecs, 1 divided by 0.00 arc seconds, and that comes out to be a distance in parsecs of 125, and you can convert that distance from parsecs into light years. So that comes out to 407.5 light years, and you can convert the light years into miles from there. And from there, I believe you would get, what is that, 5,800,000,000,000 or 880,000,000,000, 800,000, whatever. So that's how that works, and that's how you can extrapolate distances based on their parallax angles. Oops. So to further examine what that exactly means, right? So now that we know how their system works and what these angles are and the measurements and how they're applying it through trigonometry, we can kind of reverse engineer what the angles would look like based on the parallax angles that they give us for the distances. So I took a real life example here of furthest the furthest star ever observed by Hubble is claimed to be 12.9 billion light years away, or 76 sextillion, 151 quadrillion miles away. So if you reverse engineer that distance into parsecs, you can extrapolate the parallax angle to confirm such a distance. To confirm or to reverse engineer the parallax angle from the distance of 12 billion light years, we convert it to parsecs using a conversion factor of 1 parsecs equals 3.26 light years. 12.9 billion light years times 1 parsec divided by 3.26 light years equals 3.95 billion parsecs. Then we can use the formula in parsecs. We can use the distance in parsecs equals 1 divided by the parallax angle in arc seconds to find the angle. So 1 divided by the angle equals the distance in parsecs, and the parallax angle equals 1 divided by the distance in parsecs. So for the distance of 3.95 billion parsecs, the parallax angle would be, let's see. Oh yeah, it comes out to 2.53 times 10 to the minus 20, I'm sorry, to the minus 10 arc seconds. So 0.00000000253 arc seconds. Reverse engineering the triangle with a tip of 10.53 times 10 to the minus 10 arc seconds and a baseline distance of 186 million. The other two sides of the triangle would have to be 89.999999999998735 degrees. So at that point, we're not even looking at, a triangle in the sense that this is something that, converges to a point. We're looking at two parallel lines that converge at infinity to hit this angle of 0.0000000000235. And to put that into comparison, something of that size in arc seconds would be incredibly small. And so if you were to take a typical sheet of paper, which would be 0.1 millimeters thick, that would be roughly equivalent to 4,000 arc seconds. Wait a minute, does that even make sense? 4,000, so that would be a degree. So, okay, so I guess they're saying that'd be a little over a degree in terms of the thickness of the paper. So, therefore, 2.53 times 10 to the minus 10 arc seconds would be much thinner than a sheet of paper by a factor of approximately 15 billion. So, these two parallel lines go out to a distance of 76 sextillion miles, and eventually they converge into a point that's, thinner than a sheet of paper by approximately a factor of 15 billion. And that's all based on the Noble ladder, and how they've confirmed everything based on, the brightness and magnitude of stars. They basically just come up with their own system, reified it, and then built upon that reification. So to put this in another perspective, if the Earth were stationary and the sky were rotating over top of us, and we made these observations at different parts of the year, we would get the same effect. And using the assumed motion of the Earth for the baseline of the triangle, you could produce the same effect and get these get very real calculations that work out, but are actually physically meaningless, can't be confirmed, and the angles are ridiculous for the margin of error that these produce. It's insane. You could never accurately measure this, and the fact that we let them get away with it is why they keep doing it. Is why it's why they keep telling us that that this thing saw a star that's 12.9 billion light years away. It's just crazy. So to end on that and close it up before this drags out too long, we have more information on stellar parallax. Here's Jaren's video, or here's a clip I took of Jaren explaining it in more detail. Another clip he did recently in an episode of Globebusters that they just did. Whenever they encounter things like, and they talk about this in these episodes here. So whenever they encounter things like negative parallax, which would disprove the heliocentric model, they either don't count it or they just count it as a positive parallax. And you can find that in Harvard documentation. Let me see if I can pull it up real quick. Let's still see. Nope, it's the wrong one. So I can't pull it up real quick, but I'll include it at some point. But basically, it goes into detail. It's a paper explaining what to do when they observe negative parallax, which is basically like the stars going in reverse, which can't happen if the star rotation is due to the motion of the Earth rotating. Then all the stars need to rotate in the same direction. There can't be negative parallax. But they observe it, they see it, and they just count it as positive parallax, or they'll chalk it up to instrument error and they won't report it, but they'll do like a little side note and be like, hey, we observed this, but we're not reporting it. So that's stellar parallax and how they come up with distances and all that.